In this video, we're going to talk about differential equations and solving differential equations, both general solutions and specific solutions. And this will obviously connect back to the last activity that we did with slope fields. So let's start out with an example that we used in the slope fields activity. We were told that dy dx is equal to 2x minus 1, and we could work backward from there, or we could use that to make our slope field, and then we could look at the slope field. If we knew a specific point on the graph of y, or f of x, then we could draw the curve that followed the slope field, and that would be our specific solution. But to find a general solution, basically what we would do is the following. We would start by multiplying both sides by dx, and we would have dy is equal to 2x minus 1 dx. And if you were to integrate both sides of this, on the left-hand side you would get y, and on the right-hand side you would get the antiderivative of 2x minus 1, which is going to be x squared minus x plus a constant c. And again, you can verify that if you take the derivative dy dx, you get 2x minus 1 because the derivative of the constant is 0. Another example might be something like the following. Let's say we know that dy dx is equal to the sine of x, and we're trying to find a solution, a general solution to that differential equation. We would again multiply both sides by dx and get dy is equal to sine of x dx, and then we're going to integrate both sides of that, and on the left hand side we would get y, and the antiderivative of the sine is the opposite of the cosine of x plus c. And to illustrate that, I want to show you, using Desmos, the slope field for dy dx equals sine x, and how y equaled negative cosine x plus c is a general solution for that. So we're going to jump over here, and you will see that I have a slope field here, and the slope field is for what I just highlighted in blue there, which is dy dx equals sine x. And the solution shown in red is negative cosine x plus c. And if you can tell that when I move the function negative cosine x plus c up and down, it's always going to fit the pattern for the slope field. So that's why we have to have c in there. Now, what will happen eventually is we'll say something like, well, f of 0 is equal to 0, and that means we'd have to go through the point 0, 0 there that I'm highlighting right now, and that would determine a specific value for c, how much the negative cosine of x has to be shifted up or down. So we will do problems like that eventually. There are a variety of problems like this where we want to solve a differential equation, so we'll do a few here. Here's another example. Dy dx is equal to 5x to the fourth minus secant squared x. Again, multiply both sides by dx, and you will have dy is equal to 5x to the fourth minus secant squared x times dx. We're going to integrate both sides, and don't forget the constant of integration, so you're going to get y is equal to, the antiderivative of 5x to the fourth is x to the fifth, minus the antiderivative of secant squared, which is tangent of x, plus a constant c. And that's really all there is to these differential equations. We are going to get into some differential equations where we have the variable y in there eventually in later sections, but that's called a separable differential equation, but we'll deal with that when the time comes. So here are some examples of differential equations which are often called initial value problems. And basically what you're doing is you're solving the differential equation, but you're determining the value of c in that differential equation. So as an example, let's say dy dx is equal to 3 sine of x, and we happen to know y is equal to 2 when x is equal to 0. Okay, so we're going to solve the differential equation. So dy equals 3 sine of x dx. We're going to integrate both sides to solve for y, so we get y is equal to negative 3 cosine of x plus c. At this point, we have to substitute in the information that we have, and we know that when y is 2, or y is 2 when x is 0, so negative 3 cosine of 0 plus c, and as you know, the cosine of 0 is 1, so we have 2 is equal to negative 3 plus c, or c is equal to 5. So our specific solution to this is y is equal to negative 3 cosine of x plus 5. That's called an initial value problem. And for my last example, I'm going to do something where typically you're told you have to use the fundamental theorem to solve this initial value problem. So maybe you get something like this. dy dx is equal to sine of x squared, and y is equal to 5 when x is equal to 1. When x is equal to 1. And they're told to use the fundamental theorem of calculus for this. Well, one clue for this would be that, well, we don't know how to anti-differentiate the sine of x squared. So what are we going to do here? We're going to have to use the fundamental theorem to solve this. So think about what you could differentiate to get dy dx is equal to the sine of x squared. Well, if you think about the fundamental theorem, you could say, oh, you know what? I can write myself an integral here, and I can make the upper limit x squared, and I can use the sine, I'm sorry, not x squared, x, and I could use the sine of t squared dt. So as you know from the previous chapter, if we were to differentiate this, we're going to get the sine of x squared. And that's why I changed this to t squared and left the upper limit as x, because if I had left the upper limit as x squared, then I'd have to apply the chain rule, and I would have a derivative that has a 2x on it, and we don't have that. Now, we also know that y has to be equal to 5 when x is equal to 1. All right, so we're going to do kind of a trick here, and we're basically going to say, let's make the lower limit 1. So if my upper limit is 1, then my integral from 1 to 1 of anything is going to be 0, but I have to have a constant out here, and I need y of 0, or when x is 0, I need y to be equal to 5. So basically what I'm going to do is I'm going to play a little trick here, and I'm going to say, oh, well, let's make that 5. Now, if you verify this, dy dx is going to be equal to sine of x squared, okay, and the derivative of x is just 1, so even if you apply the chain rule to that, and if you verify y is equal to 5 when x is equal to 1. Now, those only come up when you're given instructions to use the fundamental theorem to solve the differential equation. But again, a tip there would be, if you're looking at a differential equation in terms of a single variable and you're thinking, I don't know how to anti-differentiate that, that might be a good clue that you would be using the fundamental theorem there. So that's it for differential equations, both general and specific solutions, or what are called initial value problems, where you solve for the value of c, and how to use the fundamental theorem to solve an initial value problem.